Yeah.
So hello everyone. In the last class, we were discussing about the capacitors. We discussed about the capacitance of a spherical capacitor, capacitance of a parallel plate capacitor also, right? The capacitance of a parallel plate capacitor is very important for you, right? And for your board exams and for your competitive exams as well. And with respect to that, we'll be discussing some of the questions related to parallel plate capacitors today. So we'll be starting with the question number 1 on the screen. The question is that the plate separation in a parallel plate condenser. When we say condenser, it means the capacitor, right? We're talking about the capacitor. So condenser and the capacitor are the same thing. So the plate separation in a parallel plate condenser is D and plate area is A. If it is charged to V volt and battery is disconnected, then the work done in increasing the plate separation to 2D will be. It means that we have this parallel plate capacitor like this. This is the parallel plate capacitor. This is the symbol of capacitor, right? Symbol of capacitor. So this is the parallel plate capacitor, and initially, it was supplied with a potential, or we can say it was supplied by a battery of V volts, right? And the capacitance of this capacitance is, let's suppose, C. And the question has been given as that the distance or the separation between the two plates of the capacitor is given as D, and the area of this capacitor is given as A. We know that for a capacitor, the capacitance depends upon the area. That's A epsilon naught upon D and the separation between the plates of the capacitor, right? So it depends upon the two things. One is the area of the capacitor, another is the separation between the two plates of a capacitor, right? So capacitance of a capacitor here will be A epsilon naught upon D, right? A epsilon naught upon D will be the capacitance of this capacitor, right? Where epsilon naught is the permittivity of free space, right? If some dielectric is placed between the plates of a capacitor, right? And if it is fully filled, then the capacitance of the capacitor is going to increase. It will be A epsilon naught into epsilon R upon D, right? In that case, we'll discuss that later also, right? But what the question is asking is that if it is charged to V volts, right? If it is charged to V volts, if initially this capacitor is charged, right, there will be some charge flowing from the battery and this capacitor will get fully charged, right? This plate will be positively charged and this plate will be negatively charged, and each of these plates will have the magnitude of charge plus q and minus q respectively, right? So what happens is that we suddenly disconnected the battery, then we suddenly disconnected the battery, and what we did is that we just increased the separation between the plates of these two capacitors, right? Plates of these two capacitors. And if we increase the separation between these two plates of a capacitor, right, then what's going to happen? The capacitance of these two capacitors is going to change because the separation between the two plates has changed. Then the new capacitance of this capacitor will be nothing. It will be A epsilon naught upon 2D, right? Now the distance between the separation has been increased to 2D. So the new capacitance will be A epsilon naught upon 2D, right? A epsilon naught upon 2D, right? So this will be the new capacitance. But the question is asking us, we have to find the work done. Now we can see why we need to do work to increase the separation between the two plates of this capacitor, right? You can see that this plate of the capacitor is positively charged and this plate of the capacitor is negatively charged, and these two plates of the capacitor are going to attract each other with some force, and what is going to happen is that these two plates of the capacitors will collide each other, right? So in order to avoid the collision or collapse of the two plates of this capacitor, we need to hold these two capacitors, right? And similarly, if we have to increase the separation between the two plates of the capacitor, then we have to do some external work in order to increase the separation between the two capacitors, because there is a force of attraction between the two plates of a capacitor, right? That's the reason we need to do work on these plates of our capacitors, so that the separation between the two plates of the capacitors increase to 2D, because these two plates are going to mutually attract each other and we need to do external work to separate them from distance d to 2D, right? So this work then will be nothing. It will be the change in potential energy of the capacitor final, right? It will be equal to final energy of the capacitor and the initial energy of the capacitor, right? So, so the initial energy of the capacitor was nothing. Initial energy of the capacitor was, it was equal to Q square upon 2C, right? Q square upon 2C, right? Q square upon 2C was the initial energy of this capacitor, and this Q charge Q is nothing, that will be equal to CV, right? CV, C into V, and this C is nothing, it's A epsilon naught upon D, right? A epsilon naught upon D. So A epsilon naught upon D multiplied by V will be the A epsilon naught upon D multiplied by V. This will be the charge. This will be the charge of this capacitor, right? Q charge, and the energy will be nothing. It will be initial energy of this capacitor will be half of or Q square upon 2. So you can write it as A square epsilon naught square V upon 2 into C, right? Multiplied by it will be A square epsilon naught square V square, right? Upon D square, right? And this C is nothing. It's A epsilon naught upon D. We can put this also in this equation. It will be A square epsilon naught square V square upon 2 times A epsilon naught upon D multiplied by, right? So this will be multiplied by D square, right? Multiplied by D square. So this square and D will get cancelled, right? And this A and A will get cancelled here, right? Epsilon naught, it is epsilon naught square here, right? This square and epsilon naught will get cancelled here, right? We'll be left with initial potential energy of this capacitor as A epsilon naught. Okay, A epsilon naught V square, right? V square upon 2D, right? A epsilon naught V square upon 2D, or we can write it as also half CV square, right? Half CV square, half CV square, right? The final potential energy will be nothing. And final potential energy, what's going to happen when we're changing the capacitance, right? We're changing the capacitance of the capacitor, right? But the electric field strength between the two plates of the capacitor, electric field strength of the two plates of the capacitor will be same, right? The electric field strength is not going to change between the two plates of a capacitor, right? It will be same. But what is going to change is that the potential difference between the two plates of a capacitor, right? The potential difference between the two plates of the capacitor will change. The final potential, the V final will be nothing. It will be equal to V final will be equal to V final will be equal to initial final electric field, that will be sigma upon epsilon naught, right? Sigma upon epsilon naught multiplied the new distance, that will be equal to 2D, right? 2D. So we can write this final potential as sigma is Q upon A, right? Q upon A epsilon naught multiplied by 2D, right? So this will be the final potential energy. And from here, we can just easily calculate the change in work done by the external agent. That will be nothing. That will be equal to final potential energy minus the initial potential energy, right? So final potential energy minus initial potential energy will be the total work done by the external agent, right? This will be the total work done by the external agent in order to increase the separation between the two plates of a capacitor, right? Two plates of a capacitor by D, right? Or increasing the separation to 2D, right? So let's move on to the next question here. A slab of material of dielectric constant epsilon r has the same area as the plates of a capacitor, as the plates of a parallel plate capacitor, but has a thickness 2d upon 3, where d is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates, right? So the question is like this. Let's suppose that we have this parallel plate capacitor is there, right? This is the parallel plate capacitor here. And if this is the parallel plate capacitor here, and the area of this capacitor is A, right? Area of this capacitor is A, and area as the plate of capacitor, but has a thickness 2d upon 3, where d is the separation between the two plates. So d is the separation between the two plates here, d, right? And the thickness of this dielectric is 2d upon 3, right? Let's place this dielectric here, and the thickness of this dielectric is 2d upon 3. The thickness of this dielectric is 2d upon 3, right? This is the thickness of this dielectric, right? So if this is the thickness of this dielectric, right, it means that the remaining portion will be this area and this area without the dielectric, right? Without the dielectric, and the only medium here in this region will be, that will be equal to t minus 2d upon 3, or that will be equal to t upon 3, right? T upon 3, right? Now the question is, where d is the separation of the plates, how is the capacitance changed when the slab is inserted between the plates? So initial capacitance was nothing, it was equal to a epsilon naught upon d, right? This was the initial capacitance of the capacitor, right? Now we have inserted a slab here, right? We have inserted a slab here, right? Let's suppose this plate of the capacitor was positively charged, it was q, and this plate was minus q, negatively charged, right? Right? And we know that in between the electric field in between in the medium or in the dielectric will be nothing. It will be equal to E equal to equal to epsilon naught sigma upon epsilon naught into epsilon naught, right? This will be the electric field, right? Or we can write this sigma as q upon epsilon naught into epsilon naught, right? This is the electric field between this region. So in this region, this is the electric field in this medium, right? So the potential difference between in this region, in this dielectric will be nothing. It will be equal to the thickness, right? The thickness is 2d upon 3 and the electric field here, right? So V will be equal to, let me call this Vg, this is the potential difference across this dielectric slab, that will be equal to Q upon epsilon naught into epsilon r multiplied by the thickness, right? That will be 2d upon 3, right? And rest of the potential drop will be across this region, right? That's d upon 3, right? And this potential will be, let's suppose this is va, let's call that as va. It will be equal to, in this region, the potential drop will be equal to the electric field is sigma upon epsilon naught, right? And multiply the thickness, that's remaining thickness, that's t upon 3, right? So the potential here will be sigma d upon 3 epsilon naught, or we can write it as qd upon 3a epsilon naught, right? 3a epsilon naught. So this will be the potential in this region, right? Potential drop in this region, total potential drop in this region, and Vd is the potential drop in this dielectric, right? In this dielectric, and the total potential drop has to be the sum of the total potential drop will be equal to the potential drop across this dielectric and the potential drop this this remaining area, right? Remaining space. So let's suppose V is the total potential drop, right? This is the total potential drop. So it will be equal to Vd plus Va, right? Vd plus Va. We can write Vd as sigma d upon 3. We can write Vd as q 2qd upon epsilon naught 3 epsilon naught into epsilon r, right? Plus qd upon 3a epsilon naught, right? And we know that the capacitance is nothing. Capacitance is equal to total charge Q upon the potential drop V. And we can replace this V with this equation, right? So capacitance of this capacitor will be Q upon V. That's 2Q T upon 3 epsilon naught into epsilon R, right? Plus QD upon 3A epsilon naught, right? This Q and Q will get cancelled, right? So we'll be having, it should be A here, right? 2QD upon 3A epsilon naught, right? So we can take this 1 upon 3A, or we can take this D upon 3A epsilon naught as common, right? D upon 3A epsilon naught will be taken as common, right? We'll be left with 2 upon, we'll be left with 2 upon epsilon R, right? 2 upon epsilon R, and plus we'll be left with, here in this case, d upon 3 epsilon naught plus 1, right? This will be plus 1. So this has to be equal to plus 1. So this will be the final capacitance of this capacitor, that is 3A epsilon naught upon 2 epsilon r 2 epsilon r plus 1 and divided by this t vector. So this will be the final capacitance of this capacitor, right? So that will be the final capacitance of this capacitor. It means the capacitance of this capacitor has increased with the introduction of this dielectric slab, right? So let's try to solve this question number 3. Let's discuss all the parts of this question one by one. A capacitor having a capacitance of 200 microfarad, right? The capacitance of this capacitor is 200 microfarad, right? Is charged to a potential difference of 20 volts. The charging battery is disconnected and the capacitor is connected to another battery of EMF 10 volt with the positive plate of the capacitor joined with the positive terminal of the battery, right? So it means that initially we had a capacitor like this. This is the capacitor. Its capacitance was given as 200 microfarad and the potential drop across this capacitor was given as 20 volts. And what we do finally is that what we did is that we have just the charging battery is disconnected and then now the capacitor is connected to another battery, right? We're connecting this capacitor to another battery, right? And that battery is of 10 volts, right? That battery is of 10 volts. Same capacitor is now connected to another battery, right? So the question is that find the charge on the capacitor before and after the reconnection in steady state, right? In steady state. Steady state means that when the capacitor will be a fully charged capacitor, right? Capacitor will be fully charged, right? Will be fully charged. Fully charged. And in this state, the capacitor will be fully charged and the charge on the capacitor will be equal to. So let's discuss part one first. Part one. So in the part one, we have to find the charge on the capacitor before and after. So before the charge, we know capacitance is nothing, it is Q upon V, right? And the charge will be nothing, that will be CV, right? And initial capacitance was as 2 microfarad, that's 200 into 10 to the power minus 6. And the potential drop was 20, right? So it means that it will have a charge equal to 4000 microcoulombs, right? This is the initial charge, right? Qi. Let me call this as Qi. This will be the initial charge of the capacitor, right? And finally, what happens is that now this capacitor is disconnected from 20 volt battery and connected to a 10 volt battery. It means now the now the charge of this capacitor is going to change. So final charge will be nothing. It will be the capacitance multiplied with the final voltage. The capacitance once again 200 microfarad, right? Multiplied by the final potential drop, that will be 10 volts. So it will be 2000 microcoulomb, right? So 2000 microcoulomb will be the final charge. It means that the final charge has decreased from the initial charge. It means that now work has been done, right? Because the charge has changed. If the charge has changed in this circuit, then work has been done. Now the question is on which the work has been done. Has the work been done on the capacitor or the work has been done on the battery, right? Now the question is that you can see here in this case, the initial charge of the capacitor was 4000 microcoulomb, but final charge of the capacitor is 2000 microcoulomb. It means that charge is actually flowing from the capacitor to the battery. It means that the work has been done on the battery, not on the capacitor, right? So the work has been done on the battery, not on the capacitor. In the second part, find the net charge flown through the 10 volt battery. So the net charge flown will be nothing. It will be the initial charge here minus final charge. So initial charge was 4000 coulomb, right? 4000 microcoulomb, and the final charge is 2000 microcoulomb. So it will be equal to 2000 microcoulomb of charge has flown, right? 2000 microcoulomb of charge has flown. So now the third part says that is work done by the battery or is it done on the battery, right? Find its magnitude. And you can see that the work has been done on the battery because the charge has flown from the capacitor. Charge has flown from the capacitor, right? Charge has flown from the capacitor towards the battery. It means that the capacitor has discharged, right? The capacitor has discharged in this connection, right? The capacitor has discharged in this connection. It means that work has been done on the battery, not on the capacitor, right? And the work done will be nothing. It will be the total change in charge multiplied the potential drop across the capacitor. Change in charge is nothing. That's equal to 2000 microcoulombs, right? Or the charge flown is 2000 microcoulomb multiplied this. That will be equal to 10, right? So it will be equal to 2000 microcoulomb, right? We have to multiply 10 to the power minus 6 factor, right? Micro factor, right? So it will be 2 into 10 to the power 4 multiplied by 10 to the power minus 6, right? So it will be 2 into 10 to the power minus 2. That's equal to 0.02 joules, right? So this much of work has been done on the battery, right? This much of work has been done on the battery. So let's move on to the part fourth, right? Find the decrease in electrostatic field energy. So once again, previously we also discussed that decrease in the electrostatic potential energy, it will be nothing, the final potential energy minus initial potential energy, right? The final potential energy is nothing, that's equal to half C V final square minus half C V initial square, right? So you can see the capacitor has the capacitance equal to 200 microfarads, right? And final voltage is 10, right? So it will be 10 square, and you have to multiply it with 10 to the power minus 6 factor minus half. It will be 200 microfarad multiplied by 10 to the power minus 6, and initial capacitance, initial voltage of the battery was given as 20 volts, so it will be 20 square, right? It will be equal to 20 square, right? So from here you can just calculate the change in potential energy, right? So this is how you can calculate the change in potential energy. And now the important point is that find the heat developed during the flow of charge after reconnection. So definitely there must be some heat developed during the reconnection, right? There must be some heat developed, and that heat developed will be actually equal to, we know that work has been done, right? And this amount of work, some part of this work will be converted into will be equal to the change in the potential energy, and some part of this work uh, will be released as the heat during the flow of charge, or flow of charge during the discharging of the capacitor, right? So this work done will be, total work done will be equal to the change in potential energy of the capacitor and the heat, right? Heat liberated. So from here you can just calculate delta H, right? Delta H will be nothing, that will be equal to, delta H has to be equal to work done minus the change in potential energy, right? Here you can, from here you can calculate the change in potential energy, and from here we have already calculated the work done. You just plug in the values of change in potential energy and the work done. You will get to know about the total heat flown during this transition or during this reconnection of the capacitor, right? So that was it with respect to the problems of the capacitor. We discussed about the charging of a capacitor. I mean, we discussed about how the charge flows from capacitor to the battery or from battery to the capacitor, and we calculated about the heat also. We discussed about the energy stored in the capacitor, and also about the effect of the capacitance of a capacitor due to different dimensions like area, distance, or the separation between the two plates of a capacitor, right? And also on the dielectrics. So how the dielectrics affect the capacitance of a capacitor. In the last lecture also we had discussed about the dielectrics, right? So this was the final result, how the capacitance of a capacitance change by using the dielectrics, right? So this was the equation, that's A epsilon naught upon T multiplied by 1 upon epsilon r minus 1 plus T. So this was the final result. If we place a dielectric of some thickness T in between the parallel plates of a capacitor, then how the capacitance of a capacitor is going to change. So this is the final result, right? If the capacitor was fully filled, then the capacitance of capacitor will change by dielectric constant times A epsilon naught upon D. So this is how the capacitance of a capacitor varies as the separation between the two plates varies, or if we introduce a dielectric medium in between the two plates of a capacitor, right? So now important point is that if we have some circuit, right? If we have some complex circuits, right? Complex circuits, in that circuit we involve different types of capacitors, right? In different arrangements, and we want to uh, reduce that circuit of a capacitor without changing the electrical effect of that circuit, right? So that's where we talk about the equivalent circuits, right? We talk about the equivalent circuits. In class 10th, you must have studied about the equivalent resistance. What do we mean by actually by the equivalent resistance? By equivalent resistance, we mean that we have to replace all the resistors of a circuit with a single resistor there, so that the total electrical effect of the whole circuit does not change, right? That means that whatever the current was produced by the battery, or whatever the current was flowing through the battery before, the same amount of current will be flowing through the battery after as well. So it means that there will be no electrical effect, or there will be no change in the electrical effect by the introduction of the equivalent resistance in the case of resistors. Similarly here, what we do in capacitors is that, let's suppose we have n number of capacitors, we have 5 capacitors, 10 capacitors, or more than 10 capacitors, right? We want to reduce this circuit, we want to reduce this number of capacitors with a single capacitor, right? We want to ease our work, right, by introducing the concept of the equivalent capacitance, right? Equivalent, it means that whatever work is done by the n number of capacitors, same work will be done, or the same effect will be produced by the by the single capacitor, and that capacitor we call as equivalent capacitor, right? So you can see here in this case we have three capacitors. One is C1, another is C2, and third one is C3, right? So what we want to do is that we just want to replace this C1, C2, and C3 with a single capacitor, right? With a single capacitor, so such that there will be no effect on the current on this circuit, right? And same amount of current will be flowing through this battery again, and there will be no change in the electrical effect of this circuit, right? So it means that's why we say that these two circuits are equivalent, right? That's why we say that these two circuits are equivalent with the introduction of the equivalent capacitance, right? So the concept of introducing equivalent capacitors or equivalent inductors or equivalent resistors is that we just want to replace whole circuit and number of electrical elements with the single electrical element, so that there is no change in the electrical effects, and will be easily able to solve or understand the circuit, right? So in the same fashion, we have C1, C2, and C3 capacitors here, right? In this fashion, right? So we want to introduce a single capacitor in place of C1, C2, and C3, such that there will be no effect on the circuit. If the current flowing through this circuit was initially I, and now we are introducing equivalent capacitor, the same amount of current will be flowing through this equivalent capacitor as well, right? So that's what do we mean by the equivalent of a circuit, right? So in this case, we'll be discussing about the two combinations of capacitors, series and the parallel capacitor, series and the parallel combination, right? In series combination, what do we have that? What we have that the two ends of the two consecutive capacitors are directly connected to each other, and or we can say that the current or the charge flowing through the capacitors is same, right? The current or the charge flowing through the capacitors is same, and if the charge flowing through the capacitor is same, it means that the same amount of charge will be there on each and every plate of a capacitor which are in series, right? So this plate will have a positive charge, and this plate is going to have negative charge. This plate will have once again positive charge, and this will have negative charge. And this plate is going to have plus Q, and this will be having minus Q charge, because reason is that same amount of current is flowing through the each and every capacitor. So each and every capacitor will develop the same charge across the plates of a capacitor, right? So plus Q will be on one plate, and then minus Q will be on another plate, right? So that's how the charge flows in case of series combination of a capacitor. Same amount of charge will be flowing all the capacitors, and each capacitor will develop same charge, right? But the potential drop across the capacitors will be different, right? We know that potential, let's suppose across V1, the potential drop will be equal to, that will be equal to Q upon C1, right? So across C2, it will be Q upon C2, right? And across C3, it will be Q upon C3. So you can see that here the potential drop or the voltage across each capacitor will be different, because the capacitances are different, right? Even if the charge is same, but the capacitances are different, so the potential drop across each capacitor in case of series combination will be different. So this is the concept of equivalent, introducing the equivalent capacitor in case of capacitors, right? Let's see how we calculate the equivalent capacitance of series combination, right? So here you can see in this picture we have three capacitors, C1, C2, and C3, right? which are in series, because the same amount of charge will be flowing through each capacitor C1, C2, and C3, right? And all the three capacitors are here in series, right? They are in series and connected to a battery that's of potential difference or voltage V, right? Voltage V, and you can see that each plate of a capacitor actually develops same amount of charge, that's Q, right? So one plate will be having a positive charge and another plate will be having a negative charge, but the charge amount of charge in case of series combination of a capacitor will be same, because the same charge will be flowing through the circuit, right? So you can see we have a battery here, right? We have a battery here. So the potential drop across C1, C2, C3 will be potential drop across C1 plus C1, C2, and C3 will be. We just calculated that. We can use the concept. See the total potential drop is actually supplied by the battery, right? The total potential drop is actually supplied by the battery. We can just replace this whole circuit with a single capacitor, right? Single capacitor, and that capacitor we call as that capacitor we call as that capacitor we call as equivalent capacitor, right? Let me call this as C equivalent, right? And the same battery V is connected here, right? Same battery V is connected here, and we call this capacitor as equivalent capacitor, right? So this capacitor will be nothing, it will be an equivalent capacitor, right? And if this is equivalent capacitor, and this will also develop the same charge Q, right? It will also develop a same charge Q here and minus Q here, right? Same charge Q and minus Q here, because same charge will be again flowing through this equivalent capacitor as well, right? So we can write this V here as equal to Q upon C equivalent, right? Q upon C equivalent. And this V, let's suppose across this capacitor, the potential drop is V1, across this capacitor, potential drop is V2, and across this capacitor, potential drop is V3. And this V must be equal to V1 plus V2 plus V3, right? V1 plus V2 plus V3, right? So we can write this V as Q upon C equivalent, right? Q upon C equivalent. And we can write this V1 as here V1 Q upon C1, right? Q upon C1 plus Q upon C2 plus Q upon C3, right? Q upon C3. So Q and Q will get cancelled, and it means that we'll be just left with 1 upon C equivalent. 1 upon C equivalent will be nothing. It will be equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, right? So this will be the C equivalent. It means that in case of series capacitors, in case of capacitors in series, the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of all individual capacitors, right? So it means that if we have n capacitors, we can rewrite it as 1 upon C equivalent. 1 upon C equivalent is nothing, right? It will be summation of 1 upon C, right? 1 upon Cn, right? From which n runs from 1 to n, right? N runs from 1 to n. So this will be the equivalent capacitance. It means if we have n number of capacitances, the equivalent capacitance will be calculated like this: 1 upon C1 plus 1 upon C2 plus 1 upon C3, and so on up to 1 upon Cn, right? So this is how we will calculate the equivalent capacitance of a capacitor, right? So let's discuss some of the features of the capacitors in series. And we can see the first important feature about the capacitors in series is that all capacitors will have same charge, but definitely they are going to have a different potential, right? They will have a different potential difference across them. It's not necessary that uh, the potential difference will be different. Let's suppose that if we have three capacitors in series and all the three capacitors are identical, right? Then in that case, the charge will also be same and the potential difference across those capacitors will also be same. But in general, we can say that all capacitor will have same charge, but can have different potential difference across them, right? And the point number second is that we can say that potential difference across capacitor is inversely proportional to its capacitance. We can see that in case of capacitor, in case of in case of capacitor, the potential difference is nothing. That's equal to Q upon C, right? Q upon the capacitance. And you can see that the charge across each capacitor in case of series combination is same, right? Charge is same. So it means if the charge is same, it means that V is inversely proportional to C, right? If V is inversely proportional to C, it means that we can write V1 ratio, V2 ratio, right? V3 ratio as equal to 1 upon C1 ratio, 1 upon C2 ratio, 1 upon C3, right? So this is how we can write the V1 ratio, V2 ratio, V3. So this is how the potential difference across each capacitor in case of series will be distributed, right? So in series combination, the smallest capacitor gets maximum potential. Yes, because we can see that in case of series resistor, we can see that the potential difference across the capacitor is inversely proportional to the capacitance. So it means the smallest capacitor will get the maximum potential, right? Smallest capacitor will get the maximum potential. So let's suppose that if we have two capacitors in series, right? One capacitor like this, another capacitor like this, right? So these are the two capacitors in series, right? Potential is V supplied by the battery C1 and C2. Then their equivalent will be nothing. Then their equivalent, you can see the equivalent capacitance of this two capacitors will be nothing. That will be equal to C1 C2 upon C1 plus C2, right? C1 C2 upon C1 plus C2. And the amount of charge on each plates of this capacitor will be same, that's Q. This plate will be plus Q and this plate will be minus Q, and this plate is also equivalent capacitor will also have the same charge, right? Plus Q and minus Q, right? So that's it with respect to the series combination of capacitor. Let's discuss one simple problem with respect to the series combination of the capacitor. You can see in this picture, right? We have three initially uncharged capacitor connected in series, right? As shown in circuit with a battery of EMF 30 volt. Find out following, right? So we have three capacitors, 2 microfarad, 3 microfarad, and 6 microfarad, and they are connected to a battery of 30 volts. And the charge flow through the battery, right? Let's suppose this Q charge has flown through the battery, right? Let's suppose Q charge has flown through the battery, right? And the same Q charge will be on each of the capacitors, right? So same charge will be on each of the plates of a capacitor, right? Charge flow through the battery. So we have to find the charge flow through the battery. So the charge flow through this battery will be nothing. It will be equal to, you can just find the equivalent capacitance of these three. So equivalent capacitance will be nothing, 1 upon C equivalent upon 1 upon 2 plus 1 upon 3 plus 1 upon 6, right? 1 upon 6. So write it as, you can just write it as 1 upon 2 plus 2 upon 6, right? Or it will be nothing. It will be equal to 5 upon 6, right? 5 upon 6. So from here, 1 upon C equivalent is nothing. It's 5 upon 6. Or we can say that C equivalent is nothing. That's equal to 6 upon 5 microfarads. So this is the equivalent capacitance of this capacitor. If this is the equivalent capacitor, then the charge flow will be equal to C into V, right? C equivalent into V. C equivalent is nothing. It's 6 upon 5 multiplied by the V. That's 30 volt, right? So it will be 5 into 6, right? So charge will be equal to 36 microcoulombs, right? 36 microcoulombs, right? 36 microcoulombs will be the charge, right? Load. And potential energy 3 microcoulomb capacitor. So the potential energy in 3 microcoulomb capacitor will be nothing. It will be equal to potential energy U, that will be equal to half CV square, right? And you know that capacitance of this 3 microcoulomb capacitor is 2 microfarad. That's 2 into minus 10 to the power minus 6, and V square. We have to find the potential across this, right? Potential across this. The potential across this will be nothing. We just calculate the charge 36 microcoulombs, right? So 36 microcoulombs. So potential across this will be V1, that will be equal to 36 upon microcoulombs upon 30 volts, right? 30 volts, right? Sorry, it will be equal to V1 will be equal to V1 will be equal to 36 the charge flow microcoulombs upon the capacitance of this capacitor, that's 2 microfarad, right? That will be equal to 18 volts, right? 18 volts. You can see that least capacitor have a highest potential drop across it. You can see that 2 microfarad has 18 volts, right? We can just write here 18 square, right? 18 square, 2 and 2 will get cancelled, right? So 18 square is, I think, 324, right? 324. So into 10 to the power minus 6, or you can write it as 324 microjoules, right? Microjoules. So this will be the energy stored in 3 microfarad capacitor, right? And total energy in all capacitors will be nothing. Total energy in all capacitor, it will be half C equivalent into V square. You can just put the value of C equivalent, right? C equivalent. C equivalent, you can just put the value of C equivalent here. That will be equal to, C equivalent was calculated as 6 upon 5, right? 6 upon 5 multiplied by V square. That will be 30 square, right? Just put the value, just compute this value here, and you will get the total energy of all the capacitors, right? You can find the total energy using the individual energy of all the capacitors as well, and then sum all the energies. But you can also calculate the total energy in the capacitor using the concept of equivalent capacitors, right? So let's move on to the next concept here. The next concept is parallel combination of a capacitor. Let's quickly try to solve this parallel combination of the capacitor. You can see that here in parallel combination, each and every capacitor will have a same potential drop across it, because they are, here you can see that they are directly connected to the battery, right? Each and every capacitor will have same potential drop across them, right? That will be equal to V, V and V, right? That will be V, V and V. And you can see that the charge Q flows from the battery, and at this point, this is the junction point. Some charge will flow here, some charge will flow in this branch, and some charge will flow in this branch. And the total charge is always conserved. We can use Q is equal to Q1 plus Q2 plus Q3, right? And let's once again try to replace this circuit with the equivalent circuit, because we just want to replace all these three capacitors with a single capacitor, so that there will be no change in the electrical effect, right? So V will be the battery once again, and the charge will be Q here flowing, right? So let me call this as C equivalent, right? Let me call this as C equivalent, correct? And this Q will be nothing, this will be equal to C equivalent into V, right? C equivalent into V. And we can also see that V1 across V, so V is the potential drop across each capacitor, or we can say that Q1 will be nothing, it will be equal to C1V, right? And similarly, Q2 will be equal to C2V, and Q3 will be equal to C3V, right? C3V. So you can just let me call this as equation 1, and let's put the value of all Q1, Q2, Q3, and Q in equation 1. We get C equivalent into V will be equal to C1V plus C2V plus C3V. V and V will get cancelled, or we are left with C equivalent as C1 plus C2 plus C3, right? For these three capacitors, right? So this is the equivalent capacitor. So, or we can say in general, if we have n number of capacitors, we can just write C equivalent as summation of Cn, where n runs from 1 to n, right? So this will be the equivalent capacitance of this parallel combination of capacitor, right? And you can see that here in parallel combination of capacitor, in general the charge flowing are different, right? If the charge flowing are different, right? But the potential drop across each capacitor is same, right? So we can say that Q1 is equal to in this case, that charge on capacitor 1, right? So charge on capacitor 1 will be equal to Q1 will be equal to, that's C1V, right? C1V, right? Which means that the charge on each capacitor is directly proportional to the potential drop across the battery, right? Common potential, right? So that's how the charge of the on the each capacitor depends, right? Or uh, we can say that the potential is constant, right? It will not depend upon the potential. It will depend upon the capacitance of these capacitors. It means that the capacitor having the large capacitance will have more charge across its plates, right? Than the capacitor having the least capacitance, right? So we can say that charge in case of parallel combination, charge across capacitor is directly proportional to the capacitance of a capacitor, right? So similarly, you can see that Q1 ratio Q2 ratio Q3 will be then equal to C1 ratio C2 ratio C3, because charge will be directly proportional to the capacitance in case of parallel plate capacitors, right? So, or we can say that C equivalent is C1 plus C2 plus C3, and it means the equivalent capacitance is always greater than the largest capacitor of a combination, right? So C equivalent is always greater than largest capacitor, right? Largest capacitor. So these are some of the important conclusions with respect to the parallel plate capacitors and series capacitors. So in case of series capacitors, the equivalent reciprocal of the equivalent capacitance is equal to the sum of the reciprocal of each capacitances, right? And in case of parallel combination, right, the capacitance or the equivalent capacitance is nothing. It's the normal summation, or it's the sum of the capacitance of each capacitances, right? That's C1 plus C2 plus C3 up to so on, right? So that's it for today. We're done with the capacitors and the capacitances. In the next lecture, we'll be discussing about the current electricity. We'll be starting the current electricity, right? So let's stop here.